Hi everyone! In this video, I will give a short presentation about the first UCAP school in cosmology. The school itself took place in Valencia and was 1 week long. In this slide, you can see some of the pictures that I took while walking around the city during the lunch breaks and in the afternoons. Even though there were 5 hours of physics lectures in the mornings, we were also able to attend 2 hours of lectures on soft skills in the afternoons. I found these to be quite interesting and helpful, as they are crucial to our development as scientists and yet are often lacking in university programs. Some topics that were discussed during the physics lectures were primordial black holes, inflation, gravitational waves, lattice simulations, statistical methods, phase transitions in the early universe, and modified gravity. All of these are extremely popular in the cosmological landscape, but in this video I will give a brief overview of my favorite topic, which is inflation. Cosmological inflation is a theory that was proposed to address several long-standing problems in our understanding of the universe. It posits that the early universe underwent a rapid and exponential expansion shortly after the Big Bang. This inflationary period, which occurred within a tiny fraction of a second, is thought to have played a crucial role in shaping the large-scale structure of the cosmos that we observe nowadays. Let's now delve into the motivation, workings, and observables of cosmological inflation. There are three main problems that inflation aims to solve. Firstly, we have the horizon problem. The cosmic microwave background shows remarkable isotropy in all directions. This suggests that regions of the universe that are now very distant from each other were in thermal equilibrium at some point. However, given the finite speed of light and the age of the universe, these regions should not have had enough time to reach such equilibrium, leading to the horizon problem. Inflation solves this by allowing these regions to be in contact before the exponential expansion. The second problem is given the name of the flatness problem. The universe appears to be very close to flat in its geometry. However, under standard cosmological models, a slight deviation from flatness would have been magnified significantly over cosmic time. Inflation naturally drives the universe towards a flat geometry, resolving the flatness problem. Lastly, we have the monopole problem. Grand unified theories predict the existence of exotic particles called magnetic monopoles, which should be abundant in the universe. Yet, we observe an absence of these monopoles. Inflation dilutes their density to a level consistent with our current observations. It's now time to look at the workings of inflation. Inflation is driven by a scalar field called the inflaton. The key features of how inflation works are as follows. Firstly, we have exponential expansion. The inflaton field has a potential energy associated with it. During inflation, the potential energy dominates over the kinetic energy, causing the universe to undergo a period of exponential expansion. Secondly, we have energy conservation. The total energy of the system, which includes the energy of the inflaton field and the energy in other forms, remains approximately constant during inflation. This is because the energy density associated with the inflaton field gets converted into the expansion of space itself. Finally, we have the end of inflation. Inflation ends when the inflaton field reaches a critical point in its potential energy, causing it to roll down the potential. This triggers a reheating phase where the inflaton decays into other particles, leading to the hot Big Bang phase that we all know about. Lastly, it is relevant to discuss the different observables of inflation, as it will allow us to determine whether our theory accurately represents reality. First and foremost, we have the cosmic microwave background and isotropies. Inflation predicts specific patterns of temperature fluctuations in the CMB. These fluctuations have been observed and are consistent with inflationary predictions. The CMB provides crucial evidence for the theory. Secondly, we have large-scale structures. Inflationary models also predict the formation of large-scale structures in the universe, including galaxies and galaxy clusters, through the gravitational clustering of primordial density fluctuations. Observations of the large-scale structure of the universe support the predictions of inflation. Thirdly, we have gravitational waves. Inflation generates gravitational waves as a consequence of the rapid expansion of space. These gravitational waves leave a distinct signature in the CMB polarization, called B-mode polarization. Detecting B-mode polarization is a significant goal for cosmologists, as it will provide direct evidence of inflation. Lastly, we have primordial black holes. Some inflationary models can generate primordial black holes, which could be detected through their gravitational effects on surrounding matter and the cosmic microwave background. In summary, cosmological inflation is a theory motivated by the need to explain certain cosmological observations and problems. It works by postulating a period of rapid and exponential expansion driven by the inflaton field. The theory makes specific predictions, many of which have been observed, providing strong support for the idea that inflation indeed occurred in the early universe. Thank you very much for listening.